Okay, so again, most of these slides are from the author of the paper. I haven't prepared them. I have made some changes and I will show, it will be indicated what changes I have made in the slides. So uh, for this lecture, we will be covering whatever was left in the last discussion, the last lecture. So we'll basically focusing on graphene architecture. So like previously, we discussed the main idea, like what is the approach, how they want to detect all those rows which are activated for a number higher than the threshold, right? And what data structures they are going to use to implement their approach. But here we are going to focus on how they are actually implementing those data structures in the hardware, right? So, where is graphene approach implemented? So they are deploying it in the memory controller. Now it answers your question. Remember your question from the previous lecture.
How about the guarantees of
No, you were saying like these entries of the table, they are also maintained in memory. So if they are also maintained,
I think it was
yeah, we'll check. Okay,
next question.
okay. So they are also maintained in memory. So if they are maintained in memory, then why they are not vulnerable to the row hammer attack? So they are implementing the graphene's data structure, basically the counter table in the memory controller, not in the memory itself. So, but it doesn't yes, they are implementing it in the memory controller, but again, it is a memory component, right? So if it is a memory component, and it is also susceptible to, let's say, electromagnet effects and the coupling, then again, maybe you can destroy the bits in the counter table itself, right? And by the way, if you can do that, then you can write a paper. that I have attacked the graphene itself. Okay. Okay. So how does memory controller perform victim row refresh? Remember they said that whenever the number of activations on a given row, they cross the threshold, actually threshold by 2. So they will refresh its neighbors or its victims, right? So, but the thing is like, yes, we want to do the refresh, but how that refresh is actually issued in real world by the memory controller. So there is no such command, because yes, you can issue the command to refresh a particular row, but you cannot issue the command to refresh victims of a particular aggressor row, right? So they introduce a new command, naming it as nearby row refresh, which refreshes the nearby rows of the specified row, not the row itself, not the aggressor row, but its victims, depending upon how you define the victim. So each NRR command, it stalls the bank in question as much as the number of rows to refresh. What does it mean? It means like, let's say this is your aggressor row, and you detect that, okay, it is activated T times in the current refresh window. So now you will issue NRR, or actually your memory controller will issue NRR. And now this, as a result of this, the victim rows will be refreshed. Now, how we define the victim rows, it depends. Like, let's say if we define only as the next immediate rows on both sides as the victim, like let's say victim 1 and victim -1. So only these two rows will be refreshed. But if you define that no, an aggressor can affect 2 rows on its both sides, like V2 and V-2, then these both of them will be, all four of them will be refreshed, right? Now, depending upon how you define the victim, your refresh operation will take longer. Here, you need to refresh only 2 rows, and here you need to refresh 4 rows, right? So, depending upon that, your memory bank will be stalled. So, but the amount of the stall for the amount of time for which it will not be available will depend upon your definition of the victim rows for a given aggressor. And when we say stall, remember we said that when you are doing the refresh operation, you cannot do any read or write operation on the memory. Okay, so detail on the paper on counter table implementation, but I would like to address some details here, because if you have read the paper, you will notify that they have modified the figure here as compared to the table. Like they have just put a block diagram, block like counter table, which is different how they have showed in the paper. So let's first talk about CAM. So why we need the CAM? So let's first create and try to understand what is the use case for the CAM. So let's consider that you have a regular RAM memory, and you want to perform the search operation. Basically, you are given let's say a 64-byte data, and you want to know that whether this data is already available, located in the RAM or not, right? Let's say in that bank of the RAM. So assume that the required data is in the memory, but in the last row of the bank, right? So if that is the case, the search operation will search all the rows of the memory in a sequential fashion. Like you will first look for the data in the first row, if not found second, not found third. Now it depends where your data is located. Let's say the worst case is your data is located in the last row. Now you need to scan all the rows. It will take time, and your search operation will be slow, right? So in the context of Graphene, if we implement our counter type table, remember, if we implement it is using a RAM, so it will be slow to search the table to find a given key. Remember how this Mr. Grease algorithm works? Like you first need to look that whether there is an entry in the table which contains this key, right? So you need to first search the table. Now, if you are storing that table as a RAM memory, so then you need to search through all the rows until you get until you have a hit. And if you have a miss, you will scan all the rows. Or even let's say if you have a hit towards the end of the memory. So your implementation of the algorithm will become slow, right? As a result, if you implement it using RAM, your solution will incur higher overhead, right? So what we have found is like if we implement searching in the RAM, the search operation is slow. So that is the motivation for the CAM, that we CAM actually accelerates your search operation, right? But before going there, here is a question. Why don't we use address of the activated row to access the counter table implementation as RAM? What I'm asking is, so remember we have this counter table and we had entries. Here we have addresses. And here we have estimated count, right? Estimated count of how many times that row has been activated, right? So if that is the case, so why don't we use the address which is when a row is activated, we know its address, right? So why can't we use that address to directly go to that entry? Just like in regular RAM, what we do, you have an address, and this address tells you, okay, which row you need to access for read or write operation, right? Why can't we do this here?
Random.
What is randomized?
Table.
Can you explain?
I'm just asking if it's randomized inside the.
Maybe you are trying to say the right thing. That's why I said explain.
Oh, okay.
Yeah.
So I was thinking about the similarity. Since it's also memory, it should be pretty similar to how ASLR works. And
No, not in that way. It's not randomized in that way. Yes.
Is it because you can evict addresses, like when the spillover count is equal to one of the other counts, you move that address into that spot, and essentially the addresses keep changing for each entry?
Okay, now let me ask you a leading question. Let's say we don't evict. We don't evict. We have high number of entries. Sorry.
If you have like a lot of addresses and if you're trying to find one specific one, would that just take too long? Would that
So
just-
why should it? I know the address, and if I know the address, I can directly go to that row in the table, that entry in the table.
Address translation?
Well, then it's not space efficient anymore, right?
Yes. It will be not space efficient because if you have a bank with 64K rows, then for each row you need one entry, right? So like you will have 64K addresses, 64K entries. Now your search will be fast, but you have 64K entries. So which kills the whole motivation of graphing, right? Okay. So because address of the activated rows change as all rows, for example, let's say you have 64K rows in a bank. Let's say all of them are activated, and each of them is activated only once in one window. So it's mean you need to maintain one entry for each row, right? So we cannot have 64K entries. And it's against the Mr. Greer's algorithm that stores items as key in the table. You don't use items as an address or index to look into the table, but as a content of the table. Okay. Okay, now in the previous slide, we talked about what is the problem with search operation performed on RAM, right? And we want to now speed up. Now, how the CAM or content addressable memory, it can speed up the search operation. So it offers the faster search operation for a given data. For example, let's say you have a given data, input data, so and then there are multiple rows in the CAM. So what you do is that you address you perform searching using input data, not using input address. So here you are saying, okay, this is data, and I want to search this data whether it's located in the CAM or not, right? So what is done that this data is at the same time simultaneously, it is compared with its content is compared with the content of all the rows at the same time, right? So which basically means that now you are speeding up the search operation, right? Not in the sequence, right? And if you find that data, let's say you find that data here, green line, then you output the address of that row, okay? And if the data is not found, then you have an output signal which tells you that, okay, you drive it high to indicate that data is not found in the CAM. But then definitely there is the drawback, right? What is the drawback? Yes, our search operation is optimized because in parallel, we are searching, not searching in parallel, what we do is that we compare the input data with all the rows at the same time, right? And then we can, in a quicker way, we can figure out, okay, if there is a row which has the same data, input data or not, right? But what is the drawback? What is the trade-off?
Is this an extra components, hardware components?
Yeah, so if you are comparing the input data with the whatever is stored in all the rows, so for the purpose of that comparison, you have to have some extra component, right? So in each cell, the size of the memory cell is larger. Each size of each cell is larger in CAM. Why? Because it has extra logic where it compares the stored bit with the incoming input data bit to find out whether these two values of these two bits are same or not. So as a result, what happens that it takes more area and it is more expensive. Okay. That's why we don't use CAM normally for holding the regular data or for regular operations, like for example, read and write operations. You use CAM only on those situations where the amount of the data or amount of the data on which you want to perform the search is relatively small. For example, let's say if your counter table is a size of 1 gigabyte, then it is not a wise option to use the CAM to implement the counter table, right? Because it will be expensive and it will also incur more energy overhead, right? Because you are using more components, including comparator bits. But at the same time, CAM also allows read and write operation. It is not only like CAM can perform only search, it also allows read and write operation. Read and write operations work in the same way as a regular RAM, but the search operation is different. It is not performed in a sequential way, but in a parallel way. Okay. So this is the figure of the graphene architecture. So let me first go over there. What they have implemented, they have deployed or they have implemented it as a part of the memory controller. So this is like the original memory controller, which is like unmodified, and this is the extra architectural component they are adding. And here what they have is like whenever they have an activation signal for a particular row, so it goes to the control logic. What is the job of the control logic? Job of the control logic is to implement that Mr. Grease algorithm, right? And for that, they are maintaining, remember, for that, we have to have two things, one counter table and one spillover counter register or spillover count. So spillover count register it is a simple register, so not a big deal. But for the counter table, this is counter table and it has two components. One is address and the other is the estimated count. So they are implementing it as a separate CAM, like they are putting it in a separate CAM, and they are putting this one also in a separate CAM. And this one is named as address CAM, and this is named as counter CAM. So here they have address CAM and counter, like two columns of that table, right? So and so now if let's say if you want to do the search, so what you will do is like whenever you have an activation for a given row, so it means you have an address of that row. So you will feed that address as an input of the CAM to this address CAM, and it will tell you whether there is an address already entry in this column or not with the same address value or not. Okay. And here they are using only to store the table, only to store the counters. And they both have same number of entries. Okay, now this is how. Oh, okay. Okay, so this is how they are using this structure, the pseudocode for how they are using this structure to implement the algorithm. So let's say you have an activation address, like and you want to activate any row. Maybe it is a normal operation or maybe it's an operation performed by a malicious user, but there is you want to activate a row and you have its address, activated address. So what you do is like you first check if you first need to look into the counter table. But in what part of the counter table? This address column, right? So you look into the address CAM. So you perform a search operation on the address CAM for given address, right? And if there is an entry with the given address, it will give you its index, in which index of this column it is located, like 0, 1, 2, 3, and so on, right? So then, so it's basically mean that you have a row head. Let's say we have a row head. So then what you need to do is you simply need to increment the counter. But counter is located in a different CAM, right? So how we know that which counter need to be incremented? It's simple because you already have the same, because they are, if address is here, the counter is also located at the same index. So you use the same index I to read the counter to perform the read operation on the count cam. Whatever value you get, you add 1 to it, and then you update the count cam by writing back at the same index. Okay. Now the second case, let's say there is no entry with the same address. So you need to first now need to check that is there any entry in this counter table which has the same estimated count as the spillover count, right? So you search the count cam with the for the value of spillover count, this thing, right? And if you find some entry, you will get its index, right? Let's say you find an entry with the estimated count equal to the spill count. So then what you do is that you increment the spill count and let's say store it in some local variable. And then you need to do two things. You need to update the estimated count of that entry which had the same value as the spill count. And you also need to increment the, sorry. So you need to replace the address of that entry, which had the same spill count. Let's say this one had the same value as the spill count. So you will just replace here with the new address. So this is what you are doing here. But how? By accessing your address cam. And the second thing you need to do is that you increment the count cam and increment the value as well. So basically you here, if its value was, let's say X, so you put it X plus 1. Okay. And but if, let's say there is no such entry which has the same estimated count as the spill count, so you simply increment the spill. Okay. Okay, what is critical path? I mean, the definition of the critical path will depend upon which component or which process you want to, for which process or the component you want to find the critical path. So for example, in our case, critical path is the longest path to update the counter table at the spillover counter. Like we are actually, whenever you have an address activation, you update these cams or you update the spillover count, right? So which one, like there are different paths. If you remember the figure about the flow of the algorithm from the previous lecture, there are different paths. Yes, no, yes, no, yes, no. So which path is like most expensive in time in terms of time latency, right? So we can figure out that by looking at this pseudo algorithm. So the most expensive path will be like, first you are doing here, let's say you are doing search. This is common for everyone, right? This is the starting point. First you have to do the search, right? And then you will do, if this is, let's say it turns out to be false, there is no entry with that given address, you are doing another search on the CAN. And if it turns out to be, let's say true, then you are doing two write operations. Write operations are expensive in memory. Okay, read and write operation, both are expensive. So here you are doing two write operations. But these two write operations, they can be performed simultaneously. Why? Because they are performed on two different cams. This is being done on the row address cam, and this is done on the count cam. So we can consider them effectively as a single write operation, right? So your critical path will be like critical longest, the path taken by the longest operation. That when it happens that this turns out to be false, this turns out to be true, and then this operation is performed. Any questions? Okay. Anyone who want to tell me why they have included this overflow bit here? What is the job or motivation of having this overflow bit? Because the count cam contains the counter, holds the counters, right? So let's say if you have like, they assume in their discussion that they have 64K, sorry. what was the threshold? They assumed 50K threshold, right? So 50K, like if 50K is your threshold, but even they still divide it even further, like 50K by 4 or 2. We did it in last lecture. Okay, let me do it quickly, check it quickly. Yeah, so 12.5K, right? So if the threshold is 12.5K, which is 50 divided by 4. So threshold is 12.5K. So it's mean that your counter should be able to count up to 12.5K, right? Now, if you will do math that how many bits you need for that, so it will turn out like, let's say it turns out you need 32 bits. I'm not sure, but I mean, you can do the math. I'm just assuming 32 bits are enough to count up to 12.5K, right? So my question was like, we are having this overflow. So this one single counter here takes 30, one single counter here, it takes 32 bits, right? So why they are putting the overflow bit there?
I can guess that it's for stability, maybe you set that to 1 and then you reset the rest, so you can go and double your number or. No.
Yeah, actually, the thing is like, remember that one particular row, it can be activated, it can reach the threshold multiple times in single reset window. If you remember from the previous lecture, right? Like in the example which we saw, they had like threshold of 10,000 and then it reaches again 20,000, right? So let's say if threshold is 10,000, you need relatively less number of bits to store this number as compared to if the threshold is 20,000, the maximum is 20,000. But we don't stop at 2T. It is possible it reaches 3T, right? Or 4T, right? So it's mean that the number of bits needed to store the total number of activations which reaches for one particular address, it is relatively larger, and we want to reduce that cost because more the bits, more the transistor you need to store that data, right? So what they do is like, okay, what we can do is like, we can have a counter which can count to the value of T, whatever it is, if 10,000 and 10,000, if it is 32, if it is 12.5K, then 12.5K, whatever it is, but single T, only T, not multiple of T. And once it reaches T, we can have this overflow bit, which is initially set to 0, but when let's say you have 12.5K activation, you have counted up to 12.5K, now you can set it equal to 1 and set it equal to 0. Which will tell you that, okay, now it is overflow. Now you don't need larger number of bits, right? So they are just trying to reduce the overhead, the area overhead of their design. Okay, they compared the graphene with the three schemes. Actually, they also compared with the others, but all the results are not included in the presentations. So here they have results for comparing graphene with para, CBT, and twice. So, and then how they actually did the comparison and what kind of platform they used. So they used a 16-core processor, and they actually used a cycle level simulation. They didn't implement on the actual because it is not possible to implement on the actual machine because you need to make changes in the hardware. So they cannot. So the only way is that you can simulate it by using a simulator. So they assumed a 16-core processor, or they simulated a 16-core processor system to count the number of victim rows, refresh, and their impact on the system performance. This is their configuration. It's not important. So we use both normal workloads and synthetic attack patterns. The question is, what do you understand from normal workloads and what's the difference between these two categories? What's the difference? Why they are defining these two different categories? Normal workload and synthetic attack patterns. Okay, normal workloads are those which are like there is no malicious user. Like let's say you are running your daily life, let's say Microsoft Word, and you are not launching any attack. But if you have Graphene deployed in your system, it will still be active, right? Even if there is no attack. But it will still be working. If it is still working and when there is no attack, there is a like benign application running. We want to understand that whether in that case the Graphene will incur some performance overhead or not when there is no attack, right? Normal application is running, and this is the case when you have the some program or some workloads running which are actually trying to launch an attack. Okay, so they want to understand the overhead incurred by the schemes in both cases, when there are benign applications are running and when malicious applications or programs are running. Okay. So they have evaluated all the four actually schemes, Para, CBT, Twice, and Graphene for three parameters. Area overhead, energy overhead, and performance overhead. When the row hammer threshold is reduced from 50K to 1.5K. Okay, so now let's first have a look at this first graph. So on the x-axis, what they are doing is that they are reducing the threshold, row hammer threshold. So they are assuming that if an aggressor row is activated 50K times in a single refresh window, then the attack becomes active or the bits are flipped. Here they're assuming that no, then there is no need for 50K activations, 25K is enough, and so on. So they keep reducing, right? And on the y-axis, they are showing that what is the table size. Like, for example, Graphene, which we have studied, what is the size of this counter table? How much, how many bits are needed to store this table, right? And they are reporting these results for one bank. So, which basically mean like, do you need 240 bits per bank to implement, let's say, the Graphene or 480 or 720, and so all these results are per bank, not the whole memory system. Okay. So, and one thing here more, you don't see a line here for Para. Why? Because Para it doesn't use any table. It is only a probabilistic approach. Whenever you close a row, you toss the coin and use if it is tail, then you refresh the neighboring row, otherwise you don't, right? So it doesn't maintain any table. So what we see here is like this green line, which is Twice, it has the sharpest increase in the size in the requirement and the size requirement of the table, like how much memory is required by its design to store the table to provide the protection. So it increases significantly as you reduce the threshold, row hammer threshold. Why is it happening so? Because they have relatively given lesser detail about Twice in the paper, but what I could understand is like the table structure of Twice is more space consuming. So, and as you reduce the threshold, the size of the table grows. So that's why like we see the sharpest increase. In the case of CBD, which was like the state of the art at the time of the paper publication. So CBT, if you remember, we briefly discussed it the last time, where you have this, every time you keep dividing the counter into half. And whenever the split happens, you issue the bulk refreshes. So that is the CBT approach. So for example, here they are using the CBT 128. So as so if you want to provide the same level of protection with the reducing threshold, you have to increase the size of the counter, a number of the counters in the CBT, right? So here they are using 128 counters, and then here double 256, and then 512 and 1024 and so on. So they are here increase the CBT needs, like you can multiply, I don't know what number it comes from, maybe 4096, right? So you need 4096 counters. And but this is 4096 counter translate into like 240 kilobyte of memory per bank, which is used only for implementing the counters, right? And here they are able to have the lower area overhead. Why? Because the number of counters they are maintaining, it must be now clear to you from a counter table, is much less, right? Because they are not maintaining one counter every row or one counter every bank and so on. Okay. Okay, energy overhead for normal workloads. So normal workloads are those where we don't have any attack happening, right? So if that is the case, so if we look for this figure B, para has the highest or the sharpest increase in the energy overhead. Why? Because para is probabilistic approach. It doesn't matter whether I am a benign user and I'm making a legal activation of the row to write my data or read my data. Para will blindly on every closing of the row will toss the coin, right? So if there is no attack, still there will be a victim refresh happening, right? And why? As I reduce the threshold, why the energy overhead increases? Because remember, we said, like, let's say if the probability of the tail, I mean, I gave you an example, is let's say 0.05%, right? So as you increase the threshold, this probability need to be increased to maintain the same level of protection, which is like there is 1% probability of bit flip, right? So if you increase this probability, let's say this was I'm just making up numbers. They have actual numbers in the paper. So let's say this was the probability enough to provide near complete protection at the threshold of 50K. Now, if you reduce the threshold to 25, this need to be P probability of tail need to be increased. Let's say 0. When I double it, it will be 0.25, right? And in the same way, if you keep reducing it up to the 1.5K, so this will also increase accordingly. Okay, whatever is the relation, you can apply that and you will get the value. So if this probability is increasing, you are saying that you are increasing the probability of the tail when you toss the coin, right? So which means you will be incurring more refresh operations. Okay, and for graphene and twice, you have very low energy overhead for normal workloads. Why? Because they have very limited number of false positives. I mean, when there is no attack, they have the number of false positive they incur is much lower as compared to the number of false positive with CBT. So CBT has more false positive, which means it detects that it thinks that there is an attack while actually there is no attack. So if it thinks that there is an attack, it will do the refresh, extra victim refresh, which incurs the energy. But here the number of false positive are much less. As a result, your energy consumption is also, overhead is also much less when there is no attack. Okay, so again, the energy overhead for the para is it increases sharply for the case when you have when there is actually attack is happening, depending upon the threshold. I have explained already why when you reduce the threshold, uh, why your energy consumption increases. But if you compare let's say graphene and twice in figure C with figure B, you see a slight increase because now you have actual attack happening and they are able to detect the attack. So whenever they attack, let's say in case of graphene, that there is a number of activation equal to the or greater than threshold, so they issue the victim refreshes, right? And remember, smaller the row of Weber threshold, you will reach the counter which lead a threshold earlier here. So earlier you reach the threshold, you will issue the victim refreshes, which means more frequent, right? I don't think I have time for discussing the remaining two, the last one, D. So the overall result is that the graphene, it features relatively low overhead in terms of area, energy, and performance. In all cases, like it is one of the lines which has lowest value at the extreme end. Extreme end is the lowest threshold, row hammer threshold. And the other thing is that price is most expensive in case of that, in terms of the area overhead, as compared to the other two schemes. And at threshold of 1.5K, row and the threshold of 1.5K, it needs 1.2 megabyte extra memory per rank if you have threshold of 1.5K. So this is like not acceptable. Your cache is L1 cache is like 16 kilobyte, right? CBT and Para, on the other hand, these two up schemes, they incur significant energy and performance overhead. So overall, what they are saying is that our scheme is good in all three parameters. At area overhead, we have no overhead. At extreme point, in terms of like energy overhead for both normal workload and adversarial attack patterns, we have the lowest or one of, let's say, the lowest energy overhead, and in the performance overhead, we are also like very close to twice. This is twice, yeah. But the problem with twice is this thing. Okay, so they have some other details in the paper, which maybe they are not that important because we cannot cover them. Our basic purpose is to cover the main problem and the main solution. Like these are, you can treat them as secondary results, right? Okay, any questions? So this is just like a summary of like what the graphene is and what advantage or what how it overperforms the other existing solution. Any questions?
Based on the graphs back in figure C, Kara went spiked up to 75%, even though it's going to the probabilistic.
Figure C?
Yeah.
What happened to that?
Instead of 20% overhead, it wrapped up to 75%. I might have forgotten the key detail, but why is that the case?
Why is going up to 75?
Yeah.
Anyone want to explain? I have explained earlier, but anyone who want to explain? Because let me show you quickly the exact numbers. I explained using the yeah, see here. So if you need, so here they are saying like if you have the threshold of 25K, row hammer threshold of 25K, the probability of the tail in case of para, remember we said that in case of para we are tossing a coin. The probability of the tail should be 0.0295, right? Low probability. But if you reduce the threshold further to 12.5K, this is doubled, 602. Even further, again doubled. The probability is doubled. So probability starts increasing. So in the extreme case of 1.56K, the probability of the tail is 0.05034. So which basically means that now more frequently when you will toss the coin, you will see the tail. And when you see the tail, you need to refresh the victim. So which means you need to refresh the victim more frequently. More frequently refreshing means you are incurring more energy because refresh operation consumes energy, right? It is just like more frequently if I switch on and off the bulb, it will consume more energy as compared to if I switch on it's only for like one time in a day, right? Any other questions? Okay, then my favorite question, what did you learn from this graphene topic? The new thing which you learned, anything new in background or related to graphene or row hammer itself. Not only graphene, like row hammer and graphene, both.
I had never heard of the Mishra grease algorithm.
Did you hear about row hammer before then?
Huh?
Did
Last week I did. Before spring break.
Okay.
For this paper, I never.
Yeah, same for me.
Seen that.
Mishra was same for me. I mean, I never. The one thing I learned is from like when you are working in a different field, you have some concepts, you can apply them into a different field if you are able to formulate the problem in accordingly. Okay. Yeah, what did you know? Anything new? Yeah. Here he already told yes.
Like, basically para, the whole systematic of that, that's not the first time I've heard of that.
Parallel what?
The probabilistic association, getting more in depth into that. Probabilistic.
Okay, think about it. I'm moving to the next question.
So I've heard about row hammer attacks before, but I think it's really cool because I kind of actually know how it works, you know? And I've actually recently, just because I'm a bad programmer, I had a row hammer error. My OS said row hammer detected. So,
Really?
yes. Row hammer, maybe I'll pull that out. Because I wrote it in C and I kept writing and clearing memory and it told me row hammer error detected and stopped my program from executing.
You must have been doing that a lot.
Yeah, I was.
It will be interesting if you can take the snapshot and capture the screen and
I will.
and share the program with everyone on the.
I'll have to reintroduce the program. It was for Rupa's,
Okay.
site.
Oh, was it for last year?
For the crypto assignment one, yeah.
Okay.
We'll see if I can replicate it. I'll share.
The Mr. Grease was new to me, but more specifically, I like the proof in the paper.
Yeah, that proving through the lemmas.
Yeah, the Limas. I was a little dissatisfied with Lima's one's proof, but I found it very interesting that the proof guarantees that the estimated cost is greater than the actual.
Actually, it answers your question which you asked
Yeah.
last time, right?
Yeah,
I mean, it's difficult because it's difficult to keep the track of the lemmas like without having proper slides. That's why I didn't discuss them, but in the paper they have shown the proof.
I just didn't, they made an assumption that row X already was in the table and then it got evicted and then went
Yes.
back instead of making two cases of if row X was never on the table and then it. Semantics.
The schemes that were used, like the counter-based and the probabilistic ones, and especially whenever they're using the two examples of like they used R as a probabilistic one, and then CBT as one of the counter-based ones. CBT, yeah. Counter-based and graphene.
So this for me, I never heard of, the role hammer attack before, so. Learning that something as simple as accessing the memory
Yes.
so many times can affect.
Without having any
physical.
special permissions.
I literally imagine the electrons, jumping from
Yeah.
one to another.
Yeah, I never heard about Rowhammer prior to this, but with last paper and this paper, I've learned a lot about how it works and technology behind DRAM, how it's pretty vulnerable and it's looking like future implementations as it continues to scale down for performance. They're also introducing a lot more vulnerabilities as the Rowhammer threshold continues to get lower. So
Okay, well, one question related to that, maybe you can think about it on your own. So will Rowhammer also work on static RAM? What do you think? First, if you don't know, try to know what is static RAM, how it is different from DRAM, and whether the static RAM is also vulnerable to Rowhammer or not, right? Yeah, and one last question again, which I asked you last time. How many of you have gone through the background slides on the memory organization? Go through this. Yeah, go through this. They are like very well designed and. Yeah, we did
So-
this.
What the books I see that DRAM is denser. So does that make it more vulnerable to?
So the problem with DRAM is, remember, it stores the data in a capacitor and capacitor is leaky. But SRAM don't use the capacitor. It holds the data in latches. Latches, they don't leak the data. So if they don't leak, then it's fine. I hope, I mean, I don't know, maybe like someone can do the work like, okay, let's evaluate the Rowhammer on static RAM, not on DRAM.
These are the networks.
the handover.
Yeah.
So that was
That was kind of tricky.
that was a lot of work.
Yeah, and that's the problem